So I start. So yeah. Okay, great. So thank you very much for being here, and well, I would like to thank the organizers of the conference for inviting me. It has been a great pleasure to be here. So perhaps my talk is a bit tangential to the interest of the guys who attend this random geometry group, but still there will be some objects like the Gaussian free field or other objects that are supposed to have a conformal invariant limits that appear. So I hope you will still be interested in it. So my goal is to talk about a specific stochastic PDE that has a nonlinearity, and this nonlinearity has to be renormalized in order to make sense of it. And we can call it the phi-4 model. But before speaking about the phi-4 model specifically, I'd like to speak about other equations that have a similar feature of having a nonlinearity that needs to be renormalized. Because in a sense, I think it captures better how the field developed recently. So the equation I would like to talk about is another intersection is that we talk about KPZ, but this is Kardar, Parisi, and Zhang. So the KPZ equation looks like this. So H is the function you want to define by this equation, and psi is a space-time white noise. And let's say that so H is a function of space and time, and actually space is one dimensional. So on our office. So actually, I wrote Laplacian and gradient, but it's just there is just one coordinate, spatial coordinate. So the thing is that you expect H to look like at a given time, and if you look at H of t dot, you expect this function to look like a Brownian motion, and it becomes very unclear what it could mean that to take the gradient of Brownian motion and square it, right? And so you may say, well, okay, this doesn't make sense, but I will regularize the white noise so that the equation is well defined, and then hopefully I pass to the limit. But if you do that, you don't really solve the problem, because still this term will go up, and your function, I mean, the sequence of regularizations will just blow up to infinity as you remove the cutoff. And a way to avoid this problem is to somehow modify the equation and decide that along the way, when you smooth out the noise, and when you remove the smoothing, you will subtract a constant to this equation, and the constant will be bigger and bigger as you remove the smoothing, and you choose it in such a way that you obtain a non-trivial limit. So in some sense, actually, instead of trying to solve this equation, you should rather think that you're trying to solve this equation. Right? So I write minus infinity, but it's just a formal way to say that you smooth out the thing, and then here you put a constant, and this constant goes to infinity when you remove the curve. So this is a very nice story, but initially it was very unclear how to solve the equation like this. And instead, people relied, so this equation has a very nice feature which enables to make progress early on. So, and it is that you can use the Kohlberg transformation. So I have to think about the correct sign. If you decide that
so this H is not invariant under multiplying by -1, right? Is H
no right?
Is H strictly positive, or
so H it is supposed to be a model for a growing interface, and invariant measures are Brownian motion. So there is no positivity thing, but But if I put h equals log u, then I want u to be positive. But that, so if I do this chain of variables, then you will solve the stochastic heat equation with multiplicative noise, and this is known to be strictly positive.
Okay, so you're just doing, this is just KPZ now.
Sorry.
This is just KPZ?
So this is KPZ.
Yeah, you're doing now. Okay, sorry, I was confused. I was thinking you were starting on something else. Okay.
Okay, but I will go to fact 4 later. It's just to introduce a little bit the context. So if you do this chain of variables, then you solve the stochastic heat equation. I mean, well, maybe it's not very important, but then what is important is that you solve the linear equation. And you can make sense of this equation basically by using Ito calculus, by using the usual Ito iteration theory. And this transformation was used by one work which I found very inspiring. It is by Battini and Giacomin in '97. They showed that if you take the weakly asymmetric exclusion process in dimension 1 and you rescale things properly, then it will converge to the KPZ equation. But the way they say it is the solution of the KPZ equation is h equals log u, where u solves this linear equation. And then to show that this discrete system converges to that, they will use a microscopic version of this chain of variables, and then study the system after this transformation. Show that after this transformation you converge to this linear equation for u, and then say that this is the interpretation. Okay, so let me write what's F for weakly asymmetric simple exclusion process. So what was F rescales to via microscopic. So this is a very nice result, and in particular, it tells you that this way of defining the solution of this equation is in some sense correct. Like you have a discrete system that is very reasonable, this exclusion process that rescales to this equation. So in some sense, you're giving a physical meaning to this equation, not a meaning that is out of range. But so maybe there are two main drawbacks. So one is that you have actually never really defined what solving this equation actually means. You just use this trick of changing variables. So no sure sense to. And also, possibly sometimes you want to study perturbations of this asymmetric simple exclusion process, and this magical fact that you have is a very nice microscopic Kohlrausch transform will break down, and then you don't know how to proceed. Right, so rely on. And if you don't have that, so what do you do? So it will be. I mean, it's desirable to have a more robust, more maybe analytic way to understand this equation. And well, major progress came out when Martin Meyer explained how to solve this equation directly. So I will not speak a lot about how he does that, but just to mention this. And in fact, so he first wrote a paper on the KPZ equation itself, and then developed a broader point of view called regularity structures, where he explains how to solve a very large class of stochastic PDEs that look like this one.
So it's in a way, so coming back to what you said before, so in the first paper it gave us a meaning to what you said, how
Yes,
to
exactly.
subtract this infinity.
Right, and then give sense of this equation directly without using the Kohlhoff transformation. And also, no. So now we move to the 5-4 model. And the nice thing with the 5-4 model in dimension 2 is that it's the simplest possible nonlinear equation where you have to renormalize things. Like you have something to catch up, you have some infinity to write down, but it's a very small infinity in some sense. So in order to introduce the 5-4 model, I would like to explain why it is in some sense an Ising model. Okay, so I will do a bit of a few formal computations to arrive at the 5-4 model. So I want to, let's say we're on a finite graph and we want to define something that looks like an Ising model, but with the spins that take real values instead of plus or minus 1. But still, I like that they mostly take values plus or minus 1. So let's imagine that they are subject to a potential that has this shape, and this is minus 1 and 1. And so at the minimal values, this is the most favorable configurations. And so typically we want to have values 1 or minus 1, but it's not a strict condition. It's just penalized to be like that. And so I look at the Gibbs measure. So it's renormalized by something. So first I want to write this potential for my variable. So let's take it as a polynomial. So let's say it's lambda I of x squared minus 1 squared. Okay, so I give myself some extra parameter lambda to modulate the strength, and this polynomial has indeed this sort of shape. So this is just the 1 point correlation, let's say, and then we want to have this Ising interaction between neighbors. So we ask that maybe I put 1/2. We have that neighboring values of the field get close, right? We want them to be close to one another. Okay. So if I look at this Gibbs measure and I let lambda tend to infinity, then I recover the usual Ising model. Right, because then I recover the strong constraint that the spins must be plus 1 or minus 1. Now for if you're willing to make write a few formal expressions, you can try to pass to the limit. Like imagine that the field now, instead of taking values on a finite graph, we'll just live on RD. Okay. So then it's, I should say, sorry. So Gibbs measure is with respect to the Lebesgue measure on the product of Lebesgue measure on the sides of the graph. So I should write product of d phi of x. Right. So this is indeed a measure, and z is here to make it a probability measure. Okay. Makes sense. So now, if I'm playing I'm trying to pass to the limit in some sense, I'm tempted to write something like this. So the integral of lambda square minus 1 squared. This will be this then, well, okay, something. Okay, and this is what I think physicists would call a phi-4 measure. So we recognize that this directed part, I mean, one way to interpret exponential minus this directed term d phi is to say this is the law of the Gaussian free field, and then we have an extra Gibbs term that changes the measure. So instead of studying this directly, a bit like for the KPZ equation, I would like to study dynamics for this measure. So instead of looking at this, let's look at this measure on the finite graph to begin with. So let's try to write a dynamics that has this invariant measure. So it's not very hard. So now I'm just thinking of phi as a function of time and the position in my graph. I should just look at the gradient flow, but perturbed by a noise. So let's call this function b phi of x. I will have the term minus b prime phi of tx. And then the interaction with the neighbor. So there's some over by neighboring x. Ty minus dx dt plus the noise part. So plus so if I'm not mistaken, you have to divide by, you have to add this factor 1 over square root of 2 beta. Okay, this gives you a dynamics that has this measure as an invariant measure. And now we can be a bit bolder and try to do it in the continuum. So either by looking at this formal expression or by pretending that we pass through the limit in this formula. So we will write that, or maybe I will write x now because later in my notation. So time derivative of x, there should be some Laplacian coming from this part. And then there is this v prime of, this derivative of the potential. So since we have chosen a potential, the dominant power is phi to the 4. So when I take the derivative, we have the power 3 here, and I don't keep track of constants now. And also the constant term in the polynomial, you can just absorb it by putting it in the normalization constant. Right? So I will not keep track of that. So maybe there is still a linear part, and then some term. Okay. So this is the phi-4, the dynamic phi-4 equation. This is what I will try to discuss how to make sense of. So as we saw already for the KPZ equation, the problem when you try to make sense of this equation is that solutions, the problem is the roughness of the solutions. Like for Brownian motion, we couldn't make sense of the derivative, and here we will have a similar problem. So I just would like to introduce some terminology to speak about how rough some distribution is. So let's say that we start with one-dimensional white noise and try to understand what is its roughness. So I could make some approximation of white noise at scale epsilon by saying that on each little epsilon interval is just a Gaussian random variable of whose variance is over epsilon inverse. So this is epsilon. And these Gaussian, they will have magnitude about epsilon minus 1/2. Okay. So you see that this is the correct way to, if I test this field against, let's say the function 1, then it's the correct scaling for the central limiter. Right, so another way to say it is that if I write psi for my white noise and I test it against the function, let's say I give myself a smooth and compactly supported function and I rescale it so that it resembles it starts to resemble a Dirac measure. Then when I rescale this phi epsilon, this is just a 2 norm of phi epsilon squared, but if I compute what it gives me epsilon minus 1. So it's just a very simple computation to see that psi, when I look at it at scale epsilon, its typical magnitude is epsilon minus 1/2. Okay. And in fact, since this variable is a Gaussian, I could as well put any power of p, and I will have up to the constant. I will have the same estimate. So we say that. So these are expectations, but if I want to do it in an almost short sense, I will manage to get that. Sorry. It's like Brownian motion with this 1/2 regularity, right? If you want to have, you will have an estimate like this for Brownian motion with epsilon here, and you deduce that it is almost 1/2 Hölder regular. Here what I'm saying is, if I test my white noise against phi epsilon, I will have a behavior in almost epsilon minus 1/2, right? So let's say that this is a definition of what it means for a distribution to be minus 1/2 minus delta Hölder regular. Okay. And I will write this space as C minus 1/2. So here we have just computed what is the regularity of this source term, the white noise. But now let's pause for a second and forget about this nonlinearity and just look at the normal heat equation. Well, to begin with, without noise. So if I just look at the heat equation, then clearly it is. If I do this change of variable, the equation is invariant. Because I have there is one derivative in time and two in space, so there is always this counting thing of two more derivatives. So now let's move to the normal linear stochastic heat equation. So because of this, we want to rescale. So the way I want to make a bit similar analysis as the one I have done on the left. So let's say phi epsilon now is my test function. Phi is a function of time and space, and so minus something. So now I want to rescale time by epsilon square and space by epsilon. So if I want this to keep an L1 norm constant, I should put 2 plus z as an exponent, right? So then by the same argument as before, when I look at how this behaves, the white noise tested against phi epsilon, this will be about epsilon to the minus this quantity 1/2, right? So b plus 2 over 2, and okay, minus some epsilon. Let me just write it like this. Minus 2. So in this new way of measuring things, the white noise has further regularity minus d plus 2 over 2, okay? Or almost that. Just below that. This makes sense. Happy with that. Okay. And also you have the white noise is also invariant under scaling, so let me just try to figure it out. Yeah, as distributions, you have this equality law between white noise rescale like this and the original white noise multiplied by the scale. So what I'm trying to argue is I want to obtain a scale invariance for the solution of the heat equation given. It's very easy to get confused when you do this scaling thing. So right, okay. So my claim is that this is the correct way to rescale the solution of the heat equation so that it is invariant. It's not very hard to see because when you compute this, well, precisely you will get an extra epsilon square, an extra power of 2 by differentiating, and so you will get exactly epsilon minus 0 to minus 1 dt minus epsilon of z applied to epsilon squared c epsilon x. And then if I've done things correctly, well, that doesn't seem to be the case. It's this up to sign. Sorry. So I did all the exponents. That makes sense. Okay. Good. So this is better. So here we said this is equal in law to the original noise. let's say you start with 0 initial condition for your equation. So if you rescale the solution like this, it is invariant linear. So in particular, you guess what the regularity of Z epsilon should be. It's exactly how you rescale it. So Z epsilon on Z. So in dimension 1, when you zoom in, you have to multiply by a big factor in order to see something non-trivial. So it's good, right? It looks like a normal function. And then the ratio is a square root of epsilon. We have the regularity just like Brownian motion. But in higher dimensions, so it should have regularity, it should be 1 minus 0 over 2. Well, almost that, but not quite that, just like with the motion. In dimension 1, you have this 1/2 regularity, and in dimension 2 it's just like the Gaussian-free field, right? And it's not surprising because the Gaussian-free field is an invariant measure for this. So in dimension 2, your object is not really a function, but just barely. And so now I wanted to show you this because now let's introduce this cubic term and see that see why we have a chance to consider it as a perturbation of the linear equation. So now x is let's forget about the linear, this ax part. So let's just look at the equation for x and try to do the same argument. So we zoom in on x and see what equation this zoomed in variable solves. Well, okay, so it's still epsilon 0 over 2 plus 1 dt minus Laplacian of x, epsilon equal to epsilon x. So we still have this white noise thing that let me call it type prime, so it has the right distribution. And then what? Then plus epsilon 0 over 2 plus 1 x cubed. And now let me rewrite it in terms of x epsilon. So we have epsilon, so we have the 3 coming from here, plus 1, so it's 4. I have a d over 2 minus 3 d over 2, so I have a minus d x epsilon to the power 3. Right. So here you see that if the dimension is strictly below 4, then as you zoom in on your solution, this cubic term just disappears. So this is the criterion for. So if d is more than 4, the nonlinearity is subcritical. So physicists will call it the super renormalizable. It means that, well, so far we don't really know how to define the equation with the x cube, but if I zoom sufficiently close, basically I know it because I will just decide that I forget about the nonlinearity in the smallest case. But, okay, so it's negligible, but still we haven't defined what it means, this x to the power 3, so So just like with the KPZ equation, we have to find a way to add counter terms so that the equation starts to make sense again. Right? So somehow we have to play with the equation until we find the right way to write it so that it actually can be made sense of. So say that we're taking say that Z is just a Gaussian free field, and I want to define powers of the Gaussian free field. Well, sorry, you know all this very well, but I hope maybe not everybody knows it. So let's say in dimension 2. So if I regularize it, and let's say for instance I'm looking at the correlations between 2 points of this regularized Gaussian free field and a square. So you know how to compute. So these two things are Gaussians, and to compute expectations like this, there is this big rule of you plot the points that appear in your. So there are 4 terms in this expression. I draw them here, and I write x, x, y, y, and I sum over all possible pairings, and each pairing gives me a term. So one pairing is like this, which will give me this term, and the other pairing like this will give me this term, that plus, sorry. Now, when you remove the epsilon cutoff, this term will let's call it C epsilon. It will diverge to infinity logarithmically as epsilon tends to 0. So this will blow up, but this will have a logarithmic correlations, and okay. So somehow this is what you want to actually capture, but there is this big constant that blows in your face, so you have to find a way to cancel it. And the way is to decide that you will instead of looking at z epsilon squared, you will look at z epsilon squared minus this constant. And now if you compute what this gives, then it's precisely made so that this term disappears. So you will just have this part that remains. And well, okay, this part has a limit when epsilon tends to 0, and if x and y become too close, you have the divergence. But this divergence just indicates that you cannot define z squared minus c epsilon as a proper function. It will be a distribution, but this kernel is perfectly integrable, so it makes perfect sense to define a limit to this as a distribution. Well, I just computed expectations, but what happened with the constants here? So when I do this against this is the term that is above. Then there is this against this, but the expectation of that is c epsilon. So I get this c epsilon squared, so -1.
Okay.
And then -1, and then so it just. And actually, so now I want to define the cubic term just in the same way, and So we have to understand a bit better what is the trick behind this subtracting the bit constant, and the trick is to write the Hermite polynomial of Z. So the first Hermite polynomial is x. Second one is this, and the third one is x cubed minus 3xt. So the correct way to take a limit is so I replace t by c epsilon in my computation. So if I do this computation of with this quantity instead of this one here, well, the big rule just works out precisely with Hermite polynomial so that things work, and this will have a limit. And we also have some logarithmic divergence, maybe to the power of 3, but the important point is that it's a logarithmic divergence, and so the limit will be C alpha for every alpha negative, right? It's almost C0. And you can define any power in this state. Okay. So now we have a fairly good idea of what is the candidate for our way to renormalize the equation. So let me write it down again. So instead of solving that, so how we will solve minus 3 infinity x. Okay, let me forget about this linear term ax that I wrote at the point. Okay, so we set up to solve this equation. And one way to encode the idea that locally the solution should have the roughness of the linear equation is to say that, well, somehow simultaneously I will solve the linear equation, and then I will look at the difference and actually solve the equation for the difference, and then interpret it back by just post-processing it. So say that we look for a solution x of the form y plus z, where y solves the difference. So application y minus and then the noise has disappeared. So basically the goal is to by looking at the difference to remove the noise because this is the most singular part in the equation. And now let me try to rearrange this bit a little bit. So Laplacian y minus, so there's the y to the power of 3. Then, okay, z to the power of 3 is not well defined. So I have to catch it back by using this 3 infinity z. So okay, that's good. And then and then there is 3y t square minus infinity. Right. So, I mean, again, it looks like a magic computation, but Hermite polynomials are made so that this works. So here you recognize what we have made sense of before, and here also, right? This z square minus big constant, and z cube minus 3 big constant. So let me write this then with some dots 3 and 2 because it's basically standard notation for V powers. Okay. So to summarize the discussion, we have observed by this scaling argument that locally the equation looks like the linear equation. So instead of trying to solve this equation that looks to be too scary for us because of this irregular behavior of the noise, we decided we would first solve the linear equation, which we know how to do because when it's linear, you just write 200 formula, let's say, and then solve for the difference, which should be more regular because we have cancelled out this local behavior. And the equation for the difference is y equals to y minus y cubed minus. Not sure if my signs were correct here. Okay. And it's not clear a priori that when you write this equation, you will manage to solve it by usual methods. And in dimension three, actually, it's not true. You still have to continue your. In some sense, you're trying to do a Taylor expansion of your X solution, and you say that the most irregular term in your expansion is this solution of the linear equation, and the second term is this y, and here in dimension 2, this y you can just make sense of it by usual methods, let's say. So this is then what I will spend some time explaining, but in dimension 3 you have to work more, and this was the achievement of higher and other people. So this method that I just sketched is due to the Prato and the Bush. So 2003, and it came much before the regular Ritchie structure and other works related to that, because in some sense, by just one iteration, you solve the problem. So what they proved was that if you pose the problem on the torus of R2, then you have local existence and uniqueness of the solution. And also, okay, so you also know that there is an invariant measure for the dynamics, so you can use it to like for almost every starting point according to this measure, you can show that the solution is well defined for all times. But it uses the invariant measure, and so okay, there were many previous works on that. Parisian Vu wrote a physics paper on this in the 80s, and then Journal and Mitter studied it. So a regularized version of the equation that is on the left. There are also contributions of Albeverio and Bruckner using the Dirichlet forms approach. So they would define weak solutions in the probabilistic sense. So it will not be given a white noise construct the solution, but just construct the solution that has the correct load. Kuevicius and Rozowski also gave a martingale solution approach, but without uniqueness statement either. So the theorem I would like to present is the fact that actually this equation has there is a solution for all times, and the solution is unique, provided you look in the right regularity space. Let's say. So, in fact, maybe I should say first, where do you expect your solution Y to live? So we have said that this term Z to the 3, it lives in every C alpha space for alpha and negative. And this differential operator, it enables you to gain 2 derivatives. So you expect Y to be almost C2. Right? So let's say you fix alpha negative, but small, and beta smaller than 2, but close to 2. Okay, this will be used to measure this regularity and give if you give yourself for the C Z, Z2, and Z3, then say continuous functions from R, let's say. With values in this C alpha space. So here I am just speaking about regularity in space. Star is this equation above. So in the way I formulated it, you should think of this statement as referring to the torus, because the way I defined the spaces C alpha, I asked them, well, I wasn't very precise, but in some sense I asked it to be uniform over the space. Right? So you cannot expect that the solution will be uniformly controlled over the whole space like that. So let's just take this statement as on the torus, but in what we've done, we also show that if you choose the right weighted spaces properly, you can actually show that there exists a unique solution in appropriate weighted spaces. Okay. So also so maybe I should be a bit more precise about what has been done in dimension 3 for the equation. So
You can just ask before this. I don't understand because I thought you said this was what D'Aprato and de Bush had done, this reduction.
yes.
And so what you did was sort of give meaning to that.
So
reduced
the
equation?
D'Aprato de Bush approach gives a local in time existence on the torus. So it's up to an explosion time that is strictly positive with probability 1, but that's it. And also it's on the torus. While here you have well-defined solution globally in time and on the full space.
Thanks.
And well, if you think that you're trying to build an Ising model, it's kind of interesting to have it defined on the full space, because then you can ask whether the invariant measures are, whether there is a phase condition. It's not really. And right, okay, so in dimension 3, I already mentioned the errors of the regularity structural approach. Yeah, there's also more recently another approach by Guminelli, Keller, and Markowski. And for this specific equation by Catelier and Chu. So their approach is based on what they call are control distributions. And lastly, there is another approach by Kupiainen using renormalization group like this. So all these methods are very general and robust in some sense, because they do not only apply to the phi-4 equation, but I mean, you can view it as a good sign or as a bad sign, but in a way, if you want to have global existence results for a nonlinear equation, there is no way that you can have a theory that applies to all nonlinear equations, because in some sense, every nonlinear equation is nonlinear in its own way. So it's a bit contradictory to these results, because there they treat many nonlinear equations at the same time. But if you wish, in some sense, these results are perturbative arguments around the linear equation. So they argue that the nonlinear part that you add to the equation can be treated as a perturbation of the linear equation. And well, you may say, but what is the small perturbation parameter? And what plays the role of the small perturbation parameter is the time until which you manage to define the solution. Okay. So now I'd like to explain how to prove that, so how to make sense of this. So in a way, I've been talking already for a long time, because we cannot define products of distributions. But you see that in this equation, there is, for instance, y squared times z, and we have only defined z as a distribution, and okay, y is more regular, but how do you make sense of these products? So this one is C beta basically for beta close to 2, but smaller than 2. And this one is C alpha for alpha negative, but close to 0. The fact is, as soon as the sum of the two exponents is strictly positive, you can define the product of this. So, okay. So I had planned to explain this a bit more, but time is running short. So actually, what is written above makes sense, and in a way, you can always, for instance, write things like this. So y squared z in C alpha is more than the constant y C beta squared z C alpha. So you can, of course, the product will be only defined in the lowest regularity of the two. So when you want to show local existence of the equation above, somehow you want to control the C beta norm of y, and you have a control of the C alpha norm of, let's say, y squared z, for instance. But then the Laplacian operator gives you regularity so that you can actually wrap up the argument and show a short-term existence of the solution. So it's like a picker iteration, or if you do it on the torus. So this was done by the laboratory. Now the question is, so let's say we are still on the torus and we want to show global existence in time. So there the technique will have to depend specifically on the equation that we're looking at. So let's say I will do a very simple trick. I will just test the equation that I write against y itself. Okay, sorry about the 3. the other terms. So I just multiplied by y integrated. So this is the time derivative of the L2 norm. Here I can write it as a positive term, and then again a positive term. And this is maybe the enemy term. Okay. If this was not there, I would have that all these positive terms are equal to 0 and be very good. Right? Because it would give me an a priori bound on the L2 norm. So how can I control this? Well, if you just pretend that Z is very smooth, then you can just say that this is an absolute value smaller than something out of Y4. So I'm just using Hurdler. So like this, and this you can absorb. You can absorb it using this part. Like you say, for instance, that if you pretend for a second that this is smaller than a constant, then you have that a constant minus integral of y4, the second half. This remains bounded, and so you have your a priori control of the growth of the L2. And if you have this, then possibly you can explain that in your picture iteration, actually things don't get too bad. Well, okay. The thing is that Z is not in L4, so you have to be a bit. Well, I don't have a lot of time, but instead of doing this naive bound, you can. You only know that Z is in this C alpha space, so you will say that it's bounded by this C alpha norm. That's the best you can do, and then you have Y cube in the dual of this C alpha space. And now you have to explain that. So here, what we have done is explain that this can be somehow caught up using a bit of this term. Now you have to explain that this Y cube term, you can catch it up by using a bit of both of these things. So just to finish, so this will give a global existence in time on the torus. And then by using similar arguments, you can show that you can extract subsequential limits when you take increasingly large tori. So it will give you existence of a solution on the full space for all times. And then you have to find another idea to prove uniqueness, but I will not talk about it. Wow, stuff.
So you were talking about the stationary measures. Are you able to prove that this converges to the stationary measure when?
So we haven't done it, no. But on the torus, I suppose it's doable. On the full space, that's not clear at all, because, for instance, what is the measure is not even clearly. So you expect that in the full space there is a.
Aren't they constructed in the 80s or 70s or something?
Right, but as far as I know, only for small coupling, like with a small constant in front of the phi. But yeah, there is a lot of work by physicists that I haven't mentioned, which is very bad, by Glim, Jaffe, Spencer, Simon, Nelson. Plenty of people did work on that, and for instance, they showed that there is at least for if you put a small coupling constant in front of the phi4, and when you play on this other constant you have that was called A at some point, and you have a phase transition between the uniqueness and non-uniqueness, just like the Ising model in the lattice. So the conjecture is if you choose the A at criticality and you rescale things, it should converge to the same scaling limit as the discrete Ising model between. But this we have to prove.
That's the conjecture in what dimensions?
In dimension 2, I'm saying.
Just in two, right?
Otherwise, it would be very boring to stay to conjecture. I don't know. I already have no clue in dimension 2 how to do it. So.
Right, you have.
I already have no idea how to do it in dimension 2. So.
So this, your approach, it doesn't work in 3 dimensions, or do you have some refinements about it?
Okay, we haven't done it, but hopefully we should be able to show that these things exist in dimension 3 also. It's just a bit more.
More questions?
Okay.
Sorry, one more. So initial data, that plays no role here.
Yeah, because I was very vague about it, but yeah, I should have put it into the picture. I was just being cool. Sorry.
But everything works.
But yeah, if you take the initial datum in the right space, then you can find the solution 4 times.
Okay, well, let's thank the speaker.